Oh, stuff. All right, so let's start off with, let's look at the solution. Everybody got their homework submitted? Okay, so let's look at the solution to that assignment real quick. Let's see, homework 2, right? This guy. Write the number that counts between 1 and 1 million. That counts the number of numbers between 1 and 1 million that are evenly divisible by 9, 13, 27, or 81. Okay, so I'm going to create a loop. Start off at 1. Keep it going as long as it's less than or equal to 1 million. Did I already do the plus plus stuff? That? Okay. So increment by 1 each time. Inside here, I'm going to need to have a counter. So before the loop, I'm going to say int count. It'll start that off at 0 because I found none of those at this point. If I mod, and what are my values? 9, 13, 27, 81. If I mod 9 is equal to 0, count plus plus. Else, if I mod 13 is equal to 0, count plus plus. Else, if I mod 27 is equal to 0, count plus plus. Else, if I mod 81 is equal to 0, count plus plus. So after the loop, we'll print out count. What should count be? Anybody remember what the answer is? Does that look right? 179,487. So this is the number of numbers between 1 and 1 million that are evenly divisible by 9, 13, 27, or 81. So this is one way you could have written it. Another way we could have written it is with a bunch of ors. So we could have said if I mod 9 is equal to 0, or I mod 13 is equal to 0, or I mod 27 is equal to 0. We talked about ors last time, right? Okay. Or I mod 81 is equal to 0. If at least one of those is true, increment count. So that could have been your whole solution like that. If I mod 9 is equal to 0, or I mod 13 is equal to 0, or I mod 27 is equal to 0, or I mod 81 is equal to 0. If any of those are true, if at least one of those is true, we'll increment count.
Are there spaces in between those lines?
I have spaces in here, but you don't need them.
Okay.
So there's a space there, not necessary. This space is not necessary, but I mean, I like to space things out. So,
but it doesn't matter. It can be either.
Generally speaking, it doesn't matter. There's some, like for instance, you can't have a space between the equal sign.
Okay.
So that's not allowed because the equal sign is a single operator. But yeah, spaces typically don't matter. White space is ignored.
But between the two vertical lines, you don't have a lot of space either.
Yeah, no space in here either. It's just two vertical lines is an or. Go ahead.
So, I mean, it's obviously true, but so like for when you make an integer, like when you type int, your integer doesn't have to be just a single letter. It can be like a bunch of letters. It's a word. Like count, like that word. Like what is?
This is the name of my variable.
Yeah, so the name can be like.
Oh yeah, so I could have it just be called I, or I could have it be a bunch of random stuff. Yeah, it's just my variable name. So a variable name follows some rules. Cannot start with a number. Cannot have spaces.
So that means that when you're typing out like a sort of like a not function but whatever the word would be, it can't like if you want a times b, you actually have to put in the star for the times. You can't just put ab because it won't multiply.
Okay, well tell me what you want to do. So you want to create an int a is equal to 5, int b is equal to 7, int c is equal to a
Times b.
Yeah, okay, yeah, you have to put the star.
Oh.
Put the asterisk like that.
Yeah.
Is that what you're asking?
Yep. Thanks.
So I get text messages and stuff. I need to make sure that none of them are more important than you.
Thanks.
Were you in class last night? No, you were watching Game of Thrones.
Yeah, no, this is the only night. I hate Wednesdays.
Oh.
This is my only night class. I like the topic. Yeah, so it's not like I hate teaching the topic. This is one of my favorite topics to teach. But yeah, just a 4-hour class in the evening, that's not my style. But then again, let's say because it's a non-traditional grad program, the better way to teach it would be like say 2 hours at a clip instead of 4 hours. I'd rather just teach 4 hours straight one night than be stuck 2 nights. It's like a trade-off. So it's at the end of the day, it's your problem, not mine. So at least you know I'm not lying to you. What was I talking about? Oh, yeah. So does this make sense? So some common mistakes that I see with things like this is if we go back to my previous solution, this guy, some common mistakes might be something like that. Having a bunch of if statements like this, because now you're double dipping. Some numbers might be evenly divisible by, for instance, 9 and 13, just as an example. Okay, so now you're counting twice for those numbers. So you'll see if I run this, you actually get a larger number. So there are, what's it, roughly 70,000 numbers in there that are evenly divisible by at least 2 of these. That make sense? So that's why you really need to have the else's in here. Now, whether or not you wrote the else if like that, actually, if you wrote the else if like this, you technically broke my rule. But now I'll add in that this is the appropriate way to write an else if. If you were really following my rules to the T, you would have said else, opening curly brace. Oh man, this is gonna suck. Hold on. Opening curly brace. Count plus plus. Like this. 2781. 2781. I got to make it even worse than this. Okay. If this, else, if that, else, if that, else. All right, so that should give us the same answer. There's our 179. Because remember, when I taught this, we go back to the slides real quick, I showed you the syntax for an if statement. It's if, Boolean expression, opening curly brace, do some logic, closing curly brace. Else, opening curly brace, do some stuff, closing curly brace. So I advertise that you should always, 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 always have the opening and closing curly braces. Well, following that rule of thumb, if I mod 9 is equal to 0, do this. Else, opening curly brace. Here's my logic inside of that opening curly brace. If I mod 13 is equal to 0, do this. Else, opening curly brace. If I mod 27 is equal to this, do this. else, opening curly brace. If I mod 81 is equal to this, do that. So let me give a little bit of an explanation with some of those things. This is not how I would ever write it, the way you see it here. Let me give you a little bit more formal syntax for an if statement. We'll do... Oh, come on. If Boolean expression then a statement. Optionally else a statement. So the curly braces are technically not required because what follows an if is the statement that you want to happen when that if is true. So when this Boolean expression is true, we should execute this single statement. Otherwise, if we did choose to have an else, we should execute this single statement. The question is what is a statement? Statements come in a lot of different forms. For example, something like A++, that's a statement. Something like system.out.println hello, that's a statement. Something like opening curly brace, a bunch of crap, closing curly brace, that whole thing is called a block statement. Okay, so what I'm advertising is it's never wrong to use block statements even if you only have one single statement inside. It's sometimes wrong to use non-block statements if you mean for both things to happen. And let me give you an example of that. So if I come back out here and I do something like if count is equal to 0, system.out.println hello, system.out.println world. What would the output of this program be?
You need one more bracket.
Oh, yeah, I do. Now what will the output of this program be? So I start off a variable named count of type integer. I start off at 0. Then I ask the question, if count is equal to 0, print out hello, print out world. What's the output of this program be? Hello world. 2 separate lines, right? Okay. I'll change count to 5. What should the output of this program be?
World.
It'll be just world. Because since this Boolean expression is true, only the statement governed by the if statement gets executed. So since that is false, this single statement here is skipped, not both of these statements. That gets back to the syntax right here. If Boolean expression, execute this statement when it's true. Else, execute this statement when it's false. So when this is true right here, we will execute the single statement following it. We always execute this statement. I just happen to indent it so it mysteriously looks like it's part of the if, but it's not. The more appropriate place to put that guy is there. But the fix for that is, let's say you want both of those lines to only occur when the Boolean expression is true. I wrap it inside of a block statement. So now everything I've highlighted there is a single statement. Does that make sense? That's why the curly braces is never wrong. So the output of this is nothing right now, because this is a false statement. If I change this back to 0 and then I run it, we'll get hello world. That make sense? So that's where it gets kind of interesting. If I go back to what we had, my crazy solution out here. I'm adhering strictly to this whole always use curly braces thing. When the reality is, if the first line of my else is another if, I could combine these two into an else, followed by a single statement, which is an if statement. Similarly, I can combine this into a single statement, which is an if statement. Similarly, I can combine this into a single statement, which is an if statement. Okay, then we have a bunch of extra curly braces here. And then a nice thing you can do with Eclipse, if you highlight a bunch of code, it's on a Mac, it's Command-I. On a PC, I think it's Control-I, or you can just right-click, go down to Source, and click on Correct Indentation, and it will fix your formatting for you. So now it looks a little bit more readable. So if this is true, do this. Otherwise, if this is true, do this. Otherwise, if this is true, do this. Otherwise, if this is true, do this. So I combine the else ifs into a single statement, even though this else is followed by this statement right there. Actually, that else is followed by this whole statement right here, which is followed by this whole statement right here, which is followed by this whole statement. So this is a lot cleaner way of writing it. But technically, with all those curly braces, it's still accurate. Kind of makes sense how the curly braces work? It's never wrong to use curly braces. In fact, I might even go as far as to say, always, always, always use curly braces, with the one exception that if you need to do an else if. Avoid the curly braces for that, otherwise your code's going to look really strange. Not wrong. We saw it worked. But it'll look strange. All right, questions about the homework assignment? Okay, and then the paper. What was the topic for the paper for this week? Solaris, yep. And was that as painful as I told you it was going to be? So, just kind of quickly, what did we determine? So here was the question. Write a 3 to 5 page paper describing the use of Java in the first Intel version of the Solaris operating system by Sun Microsystems, now Oracle. Paper should contain at least the following topics: performance, security, hardware compatibility, and user experience. What did you come up with for me? So, how did using Java in the how was Java used in the first version of Solaris? First Intel version of Solaris. What'd you find out about that? Was it used a little? Was it used a lot? Was it somewhere in the middle? How heavy was Java incorporated into the first Intel version of Solaris? Huh?
Somewhere in the middle.
Okay. I think somewhere in the middle is fair. I would say somewhere between somewhere in the middle and too much. So Java was well represented in the first Intel version of Solaris. So what should that mean for performance? Well, slower performance, enhanced security. So it should mean the performance is going to take a hit because now your operating system is actually running at least partially within a virtual machine. So there's a middleman there. So performance should suffer. Security should be beneficial, right? Because part of your operating system is encapsulated inside of a virtual machine. What about hardware compatibility? This should have been a relatively interesting topic.
Hardware compatibility was better
Okay.
compared to Solaris 2.0
Okay, I would agree with that. Why?
because the execution of the processor,
Mm-hmm.
the execution time was the runtime, so it will save a couple of copies.
Okay, well, right off the bat, you should have increased hardware compatibility simply from it being an Intel processor. More pieces of hardware had drivers written for the Intel architecture than had drivers written for the Spark architecture, which predated the Intel version. So right off the bat, you had a better chance of having more hardware work. And maybe I'll put it this way: more hardware work well. Because software drivers were written for each of these different pieces of hardware to make them work at their, let's say, peak performance. So that's one side of the coin. Now, how did Java's role in the operating system lead to better hardware compatibility? See, something you get out of Java is you don't get these specialized compatibilities. You don't get a hardware driver specifically written for a very special piece of hardware that makes it work as optimally as possible. But Java is very good at generalizing, or let's just say generally working for a large classification of hardware. So hardware that previously would not work at all might function at a minimalist level under the Java virtual machine. So can we call that hardware compatibility if it at least sort of works? Sure. Maybe the best example of why that's problematic would be, let's say you go out and you get you have a gaming PC at home, and you go out and you buy the latest, greatest NVIDIA or ATI $800 graphics card. Go out to Best Buy, whatever, you buy this graphics card. You come home, you plug it into your computer. Let's just assume your computer doesn't know about this because it's too new. It came out tomorrow. Okay, the thing came out tomorrow. But you choose not to install the hardware driver that came with it. So, NVIDIA is going to come with a CD or at least drive you to their website to download the latest drivers and all that stuff. But you don't install that. So now you have this $800 piece of equipment sitting inside your computer that Windows 7 or Windows 8 is detecting as a standard VGA graphics card. Okay? So $800 piece of equipment that it's pretending is a $3 piece of equipment. Because that is the minimum common denominator that it could figure out that hardware is. Because that's very specialized hardware. That it needed very specialized software to teach the operating system how to make it work at its optimal level. But rather than your computer not showing any video output, it said, hey, at the very least, I know you're a beast. I know you're $800 worth of awesome. But at the very least, you were a VGA compatible graphics card. You're a lot more than that, but I can at least treat you like that, and my people can see something on the screen. So if you don't install that hardware driver, you have an $800 bone anchor that can technically show 256 colors to the screen, instead of the zillions of colors and all sorts of hardware acceleration and the 512 cores of floating point math and all this other crap. So that would be a good example of something that technically is compatible, but is a far cry from performing at where it should be performing. So that's one thing to kind of keep in mind when in this particular case, you may have seen some things where it said Solaris for Intel has tons of hardware compatibility. Some of that, it might be because of the Intel drivers, but some of it, they were blaming on Java, saying, well, Java brings all this compatibility to the table. Compatibility is a little bit of a gray area there, because some of that compatibility might be what I just discussed. $800 graphics card looking like a $5 graphics card, because it was just operating at the minimum compatibility level. but technically it worked. So technically it was compatible. That makes sense? Okay, and lastly, what about user experience?
enhanced
Okay, tell me why.
graphical, 3D and
Because of its reliance on Java and because of the applet technology that we talked some about last time, right? We talked about applets last time.
Yeah.
So because of some of those things, they were able to incorporate visual bells and whistles that previous operating systems really didn't have by leveraging the Java virtual machine. So one could argue that the end user experience was visually better because it really acted more like one of our more modern operating systems. So like you get Windows 8, for example. And as long as you have a fast enough computer, when you click on stuff, things seem kind of alive, right? Things are swishing around the screen. You have little things dancing over here, like on Macs, for instance. When a program wants your attention, what does it do? It hops around on the bar. You didn't have those back in the Solaris days. You didn't have that kind of computational power. But with Java, you could sort of have little, half solutions like that because of the little widgets that Java brought to the table. So you probably had an older operating system looking closer to our modern operating systems that other operating systems that were around at the same time looked like. So I think you could argue that it had an enhanced user experience from that perspective. Now, can you make an argument that the user experience was worse? So I think you could because of Java. I think you could say that the user experience was also worse from a performance perspective. In many ways, the operating system may have felt sluggish because Java was so heavily relied upon. Okay? Because again, every single thing you do is going through some sort of middleman to get processed. All right, that kind of makes sense? So that's kind of the scoop on Java in Solaris. And really almost it's something of historical significance because it was our evidence that Sun went through this time period. Well, really, I mean, very much Java was probably the best and the worst thing that Sun ever made. It was, from a historical perspective, a great technology that is used heavily today. But from Sun's perspective, they really never figured out what to do with it. So they took something that all the bells and whistles should have been going off, all the alerts should have been going off that Java doesn't belong at the core of an operating system. That's not where it shines. Yet they threw it into an operating system. Not only did they throw it into an operating system, they threw it into their first operating system they tried to put on the Intel platform. And what were they doing when they put that operating system on Intel? Who were they trying to compete with? When Solaris finally said, okay, we're going to move in the direction of Intel rather than stick with our Spark chips, who were they trying to compete with? Who was the somewhat cool kid on the block that was not Windows and not Mac, but running rampant on Intel, Linux? So really, there was a big Linux movement at the time where Solaris said, we are like the professional Linux. We've been around forever. We're Unix, which is, Linux, basic Unix, Linux, same thing, but Unix usually costs money, Linux does not. So we're the same thing, but we've been around for a while and we have Sun Microsystems name behind us. If we can jump over to Intel and we can get those Linux users picking us as their premium Unix experience on Intel processors, maybe we have a shot of hanging with the big boys, namely Windows being, the biggest one, and then Apple being number 2, but a far cry from Windows. So that was really their motivation. Never really took off. Maybe in their defense, Linux never really took off to that extreme. Linux today is probably about as popular, maybe even less popular, as it was 10 years ago. I don't think it's gotten more popular. It's probably either the same or a little bit less popular today. Interestingly enough, one could argue that covertly, Unix has become more and more popular because modern day Mac operating system is based on Unix. So I can open up a terminal right here, and this is the Unix terminal. I'm issuing Unix commands there. So Mac OS is like a modern day Linux distribution or modern day Solaris distribution. It's Unix with Macintosh's pretty front end on it. That's what Mac OS X is today. So I think this is probably a big reason why Linux never really took off, is because Apple probably noticed that, hey, we're really not going to compete in terms of numbers with Microsoft. You couldn't. Microsoft had such a big lead that you're going to have to wait for the way people use computers to change. You're not going to have to, you don't wait for them to lose their desktop dominance. You wait till desktops become less important. And we move on to mobile platforms in order for Windows to ever take a back seat. But what Apple did is they built their next operating system on Unix technology. So I think a lot of those Linux users, once they got done playing with the Linux technology, because one of the cool things with Linux, when I was in high school and stuff, I used to be a big Linux user. You really felt like you were using your operating system. Like sometimes you had to compile new programs and stuff like that. But at some point, that gets boring, and you want to just be able to accomplish what you want to accomplish on your computer, right? So the Mac OS is like Unix for people who actually want to get crap done, because it just works, as opposed to you having to, a new update came out today. All of a sudden, my graphics card doesn't work. That kind of stuff happened with Linux because it's an open source community. Okay, so any questions about the report? That's kind of our high level response to that. All right, so let me see where we've been. Okay, so we talked about that. Character sets, if statements. Talked about the different kinds of loops. We talked about variable scope. We talked about garbage collection at least a little bit. We talked about typecasting. All right, so let's do this. We're going to talk about methods. A method. Historically, methods were, here's some synonyms for methods. We had something called subroutines. Those are synonyms for methods. We had procedures. We had functions. Okay, so those are all synonyms for methods. Now, what are methods? Methods are reusable chunks of code that can take 0 or more inputs. I'll put in parameters. I'll put in parentheses here. Parameters. That's what they're officially called, parameters. And may return 0 or 1 value. So you can choose for a method to actually return a value, give an answer, or you can choose for it to not return a value. All right? So methods are reusable chunks of code that can take some inputs, some number of inputs, do something with them, and either spit an answer back or possibly do something with it, display it to the screen or something like that. Okay? So methods are our means by which we can write something and we might want to do multiple times. We encapsulate it inside of a method, a reusable chunk of code, then every single time we need to solve that particular problem, we call upon that method. Okay, that makes sense? Let's talk about syntax for methods. Method syntax. Okay. Starts off with return type, followed by method name, followed by opening parenthesis, followed by comma, delimited params, followed by a closing parenthesis, opening curly brace, logic, closing curly brace. Okay, so that's the generalistic syntax for a method. Return types can be anything. So let's do with this. Can be any type that we could create. Yeah, I didn't kick it down. Any type that could be used to create a variable. Let's do that. That could be used to create a variable. So return types can be any type that could be used to return a variable. As far as what we know right now, those are the primitive types. Right? What's a primitive type? Talked about these, right? Somewhere way up here. These guys. There's our primitive types. What are primitive types? If you had to give a concise definition for a primitive type, what would you say? Variable type built into the language, which is only capable of holding a single value. So primitive types are kind of like our mini variables. So return types can be anything that could be used to create a variable. Up to this point, from our perspective, that's only the primitive types. But there's also object types built into the language, as well as we can create our own object types. So literally, return types could literally be an infinite number of different things, since we can create our own objects. As far as we know right this exact moment, the only valid return types are the primitive types, because that's all we know about. Make sense? We'll know about a couple more things today. All right, so that's what the return types can be. Similarly, the parameters are also types that we can create variables. And then logic is whatever we can have if statements, loops, whatever we want to have in there. All right, so this is the generalistic syntax for a method. Now let's look at an actual method. So I'm going to go ahead and get rid of everything in main in our program here. So I'm going to create another method inside of my class. All right, so main is a method. This guy's a method, returns nothing. So to add on to this, return types can be any type that could be used to create a variable, or void if we do not intend to return something. So if we're going to have a method that returns nothing, we set the return type to be void. And this is actually related to this previous slide with the different types, synonyms for methods. If we go back to a little bit of older language, non-object oriented language like C, methods were split into two separate things. One was called a procedure, the other one was called, I don't know why I called it procedured. This is a procedure. Hello, relax. So in a language like C, we had procedures and we had functions. A procedure was something that did not return a value. A function was something that did return a value. So those got squeezed into a single term called a method in object-oriented languages, where methods had a return type, a void, when they didn't return something. Make sense? Okay, so we're going to create a method here.
We have 10,000 new emails.
Yeah, probably. You get a lot of emails. And I have like 20 different email addresses from all my different companies, and yeah, it sucks. I started ignoring them about 3 years ago. Okay, so there's some crap in here that for right now we're just going to ignore. Pretend like you never see the word public. I won't put it on my methods right now because we don't need it. Sometime during this course, you'll know what it means. Okay, so just forget that it even exists. Also, forget about this word static for right now. I promise you by the end of this course, it will be ingrained in your soul, the difference between static and non-static. But right now, we're just going to pretend like everything's static just because. Okay, I can't show you what's behind the scenes yet because you don't know this stuff. So for right now, every method we create will just magically have the word static in front. For no good reason other than that's how we do it. Okay? I'll fill in that blank later. This particular method I'm going to write is going to have a return type of void. I'm going to call this method display hello. And this guy's going to take no parameters. So notice it has the parameter list, open and close parentheses, but doesn't actually take any parameters. So to connect it back to our syntax in our slide, syntax is return type. What's my return type here? It's void. Followed by method name. My method name here is display hello. Followed by an opening parenthesis, right here. Followed by a comma delimited parameters. I'm not giving this guy any parameters, no inputs. He doesn't need anything to work. I'll show you some with parameters here in a moment. Followed by a closing parenthesis. So this guy has exactly 0 parameters with a closing parenthesis at the end, but these guys are required. Opening and closing parentheses are part of the syntax. So this guy right here would be known as the empty parameter list. Well, really, it's the parameter list and it just happens to be empty. And then, of course, opening curly brace, closing curly brace. And the opening and closing curly braces are 100% required for methods. They're not optional like if statements and loops. But like I told you, if you just always put the curly braces, except when you do else ifs, life will be easy. At least easier. Okay, so we're going to put logic in here. So the name of this method is called display hello, and all this guy's going to do is display hello to the screen. So here's a reusable chunk of code, and whenever I want to display hello to the screen, I call upon this reusable chunk of code. That make sense? Okay, so now we have to learn how to call our methods. Now I'm going to let you in on a little bit of a secret with the word static. But I'm not going to give away the punchline yet. Static. Oh, by the way, you keep hearing your computer reboot. Apparently this computer here is very sick. I got an email about it today, and Dr. Locklear is like, oh, don't use that computer, or at least come in with a backup plan or something. I never use it anyways, but that's what you keep hearing. I think it's just in a constant loop of death. I almost would just shut it off, but it's possible somebody's remoted into it right now trying to fix it, and that's their rebooting sound. Just deal. Static means that something is a class member. I'm just going to say class member. Where a member is either a field, which we don't know what those are yet, constructor, which we don't know what those are yet, or method. We're just learning about those. So from our perspective right now, anything with static in front of it is a class method, whatever that means. Okay? Now, I can't really explain what a class method is until we can talk about the other kinds of methods. But for right now, I'm going to tell you how to call class methods. But what we've done here is we've at least introduced the ability to identify class methods. We know that this guy is a method. Why? because it has opening and closing parentheses on it. It follows the syntax of a method, right? That guy's a method. What kind of method is he? He's a class method because it has the word static up front. Whatever that means. I'm not filling you in the... I'm not going to tell you what a class method is yet. It's not time. You have to wait for the season finale. Not even the season finale. Maybe next class. Probably next class. All right. Actually, no. This class. Soon. After these commercial breaks. All right, so maybe the second half of class today. We'll see. So in any case, this guy is a method. Specifically, he's a class method. Why is he a class method? Because he has the word static up front. That's the only thing that makes him a class method. Okay? So class methods. These are methods with the keyword static before their definition. There's really two states that a method could be in. We could be looking at the method definition. We could also be looking at a method being used, being called. We're going to see that here in a second. So this first statement I'm saying here is specific to when you're looking at the definition of a method, the point where it's being defined for the first time. That's what we see right here. This is the method definition. This is an untapped resource. I've written a method here called display hello that I could call, but I've never actually called. Okay? So I've defined a method, but I have not used it yet. So what I have highlighted there is the definition of a method. So when we see the keyword static in front of a method definition, that makes that guy a class method. Okay? So class methods. These are methods with the keyword static before their definition. These are methods that are called using the name of the class in which the method was defined. When we see them being called. No, it's really just what I said before is good enough. These are methods that are called using the name of the class in which the method was defined. So two different ways to identify class methods. We can look at the method definition and look for the keyword static, or we can look at a method being called and see who is calling it or how it's being called. Because class methods are always called using the name of the class in which the method was defined. The name of this class is driver. This method was defined inside of a class named driver. So we would call this method by saying driver dot display hello. So I'm going to go into main because all programs begin and end with main, and I'll say driver dot display hello. So this is where I've defined my method, and now I'm actually going to use my method inside of main. So the name of my method is display hello. It requires me to pass it 0 inputs. So I've given it the parameter list, but I haven't put anything in there. And because it's a class method, because it was defined with the keyword static out front, I call it using the name of the class in which that method was defined. It was defined inside of a class named driver. Go ahead.
But you defined the thing, the method underneath the first thing that calls upon it.
Correct. Yeah, it's a good point. So you're saying you would be less confusing if I put it up there.
Yeah.
Right? Okay, so it's actually a very good question. Let me take a second and explain this. Historically, older languages, let me put this in the notes. Remember we talked about compilers? Some languages are compiled languages, some languages are interpreted languages. Well, a compiler goes through the syntax, the source code for a language, as part of its process of translating it into a low-level language. Well, In the early days of compilers, we had something called single pass compilers. So for instance, old C programs, you'll see a lot of this evidence back then with single pass compilers. And what you would see then is, let's just assume that I actually wanted to put my definition of display hello at the bottom. Let's say I actually wanted to implement it down here. They would require us to, at the top, prototype it. At the very least, make it that the rest of the program is aware that a guy that looks like this exists, so that when the compiler goes through main and sees you calling this guy, it at least knows that you intend to implement it. Because the compiler is checking also for syntax errors. So in single pass compilers, you would have had to do one of two things. You either need to make sure that you define functions before you use them, or prototype them before you use them and then make sure you define them later. So these are our older languages. More modern languages use a multi-pass compiler technology. So what they do is they go through on a first pass and read in all the different functions that are going to be defined. So they build up a list of those functions. Then when they actually go through the second time, so when it actually goes through and looks at the inside of main, it already knows about display hello, because in the first pass of the compiler, it read it in. Kind of make sense? So in modern day languages, the order that you define methods is not important. Historically, it was. In fact, any of you ever used a language like C or C++? Something in those languages that you very well might run into, so it's worth talking about, is you will have, in the C language, you have .c files, and you also have .h files. The C file, this is the implementation. The H file is the header file with all of the prototypes defined. So what would be kind of common in a C file is you would have a C program, is you would have in your implementation file inside the .c file, at the very top, you would have #include blah.h, where blah is the name of the program you're writing, the name of your class. And that H file would have all the prototypes in it. So instead of at the top of your program having all these things prototyped, you would actually have a separate file, a header file that had all your prototypes in it. Then at the very top of your implementation file, you would have include my header file to get all my prototypes. That makes sense? Modern languages don't require that. An actual interesting thing for any of you who end up taking our iPhone programming class in the grad program, we use a language in there called Objective-C. Objective-C is very interesting. I think it's a great teaching language after you have a decent foundation in Java, because it shows you a lot of details that Java hides from you. But what's interesting about Objective-C is it looks like an old language, but it functions like a modern language. So for instance, it's very common, modern day Objective-C programmers, to use header files as well as .m files, which is the Objective-C extension. So .c, .java, .m. So I write a lot of iPhone programs, I write a lot of Objective-C software. I always use header files. Totally not required. You don't need to use them. But because we've been using them for so long, it's actually ingrained in us to use it that way. And in many ways, header files are very beneficial. Just because you don't need them doesn't mean you shouldn't use them. Doesn't make it faster. But what a header file does, if you think about a big program, the actual implementation file is going to be thousands and thousands and thousands of lines of code.
And if you put something in there and it's a syntax error, you gotta find it. Is that a problem?
Well, that's true anywhere. That's true regardless of whether you use a header file or not. But the header file itself is kind of a summary of your program. Here is all the crap my program does. Not how it does it, but this is what it does. Here's the name of my 40 methods. One per line, without any extra code in there because I'm implementing the code in the other file. So that header file becomes kind of almost the cliff notes for your program. So when you need to go and open up somebody's source code that you haven't worked with before, you can look at the header file and get a pretty good idea on what does what. Because a lot of times they'll put comments in their header file that says, this function, this is what it does. Go and find it in my implementation page. It's 300,000 lines long and it's a nightmare. But right here it looks nice and benign. Kind of make sense? So I really enjoy Objective-C from a teaching language perspective because it very much has roots in older languages like C. But nothing requires you to use a header file for it, even though everybody who writes Objective-C does. Just as a convention. Because I promise you, any compiler written in the last, it's probably fair to say 20 years, but let's just say 10 just so I'm not made out to be a liar. Okay? Any compiler written in the last 10 years absolutely is a multi-pass compiler. Okay? It doesn't matter what order you define things in. As long as they're syntactically in correct places, it will figure out that the function you're calling up here is defined later on. Because when it did its first pass, it figured it out. Okay? So that's kind of the punchline. But it's a good observation because it is intriguing since all programs begin and end with main. When I come in here and I go to this very first line of main and I'm trying to call this display hello method, well, I've never seen that guy. Well, he's defined down here, but you're using him up here. How does it know about him? Modern languages with multi-pass compilers, it knows about it. Okay? Now, let's assume that you don't get to see this guy down here. You don't get to see him. Okay? So, can I make him go off the screen? Haha! You don't get to see him. Is this the class method? The answer is yes. Why is that a class method? Based on what we just talked about. Go ahead.
Because you called it with the name of the class and the name of the method.
Okay. So, for starters, if I promise you this guy is defined somewhere inside this class, I've called this method using the name of the class in which it was defined. I called it using driver dot. Here's the name of my class. So since I said driver dot out front here, that must mean this guy is defined somewhere inside this program, inside this class. Now, before I even consider that though, how do I know this guy's a method? How do I know that what I have highlighted right there is some kind of method? The parentheses, the parameter list. So the fact that it has opening and closing parentheses here means that it's a method. Technically, it means it's a method or a constructor. I promise you it's not a constructor, and you'll know why when we talk about constructors. Go ahead.
So that makes main a method? No, it doesn't. It's not even called a class.
Main is a method, but this is a method definition. Somebody else is going to call this guy. All programs begin and end with main. So the Java virtual machine calls this main method.
Gotcha.
Okay, so this is a method definition.
All right.
That's why we have the word static out front and all that crap. That make sense?
Yeah.
Okay, so we know it's a method because of the parentheses. We know it's a class method because we're calling it with the name of the class in which it was defined. Because right here we're seeing the method being called. Down here is where we see the method being defined. And we know it's a class method because the keyword static's out front. Make sense? Okay, so if I run this program, what it'll do, all programs begin and end with main. It'll come here to the very first line of main. It'll call the display hello method, passing it no parameters. That'll transition down here. And what does the display hello program say to do? It says print out the word hello. So that's what the output of our program will be. It'll print out hello. Make sense? Okay. Give me a second here. Spit out this gum. It's had better days. All right, so that's a very simple method. Similarly, if I want to call that method multiple times, remember methods are reusable chunks of code. I'll call it 4 times in a row inside of main, and we'll see it prints out hello 4 times. If I want to say system.out.println world as just hard-coded lines inside of main after each call to my method, it'll print out hello world. Because what's it doing? It's calling this method, which says print out hello. Then it's going to this line, which says print out world. Then it's calling this method, which says print out hello, print out world, so on and so forth. Go ahead.
So then what are the system and out, those must be methods too.
Correct, they are. Yep.
Then where are they calling from?
Well, I'll only give part of the punchline here, because we'll actually talk about this quite a bit when we talk about instance methods. There exists a method called println. How do you know it's a method? Because it takes an opening, it has an opening closing parenthesis. It's called by something called out. We don't know what out yet is, but I promise you out is an instance of something. We'll talk about it. And out actually belongs to a class called system. So we have a class calling an instance variable within that class, which calls one of its instance methods.
But you didn't define any of them.
Because they're built into the language. System.out println is part of something called java.lang. So out in front of here is java.lang.system. That's what that actually is. And I promise we'll actually explain all that. Okay, but that's where it comes from. So for right now, it's just built into the language. Okay, it just works. That's how you print something to the screen for right now. We'll talk about why it works that way before too long. Okay, so does this make sense? I'm calling a method that I wrote myself. Then I'm using a method that was written for me built into Java. Called a method I wrote myself. Then I'm calling the println method that was built in to print something to the screen, so on and so forth. And that's where we get our output here.
If you want them on the same line, you just don't put the semicolon.
Well, if you don't want them on the same line, or if you do want them on the same line, then you'd want to take the lin off of that guy and put a space.
Oh yeah. Okay.
Then you'll get hello worlds. Because println kicks it down a line. So if I just have my display hello, print hello followed by a space, it'll leave the cursor at the end of that line. Then when I do println, it'll print out world and then press return. All right, so I'm going to go ahead and I'm going to get rid of most of this code for a second here. I'll go ahead and put the lin back in. That way it's on separate lines. So we'll incorporate a loop here. So I'll say for int I is equal to 0, I is less than 10, I plus plus. I'll call my method 10 times.
Wait, you forgot to print limits typo.
Yep. There you go. So I have my method defined. Now I wrote a loop, and this loop's going to go through 10 times. What's it going to do each time? It's going to call my method. So it should print out hello 10 times. So I'm using my repetition, one of my loops, in conjunction with calling a method that I wrote. So there's hello 10 times. Make sense? Now, an interesting little thing to throw in here. It always comes up in class at some point, but I just remembered it now, so I'll bring it to your attention now. Let's say I'm going to create a count. I'll start count off at 0. I'm going to spin through 100,000 times. each time through, I'm going to say count plus plus. I'll add 1 to count. Okay? Then at the very end, I'll do system.out.println count. So what does main do? Remember, all programs begin and end with main. Main says define a variable named count, start off at 0, create a loop that goes from 0 to 100,000, not including 100,000, incrementing I each time. What are we going to do in the loop? We're going to increment count by 1 each time. So count goes from 0 to 1, 1 to 2, 2 to 3, 3 to 4, all the way up to 100,000. What do we do at the very end? We print out count. So as this code's written right now, this method is an untapped resource. It's there for us to use if we want it, but we're not actually using it in this program. Okay? So the output of this program should be what? 100,000? 1 time, correct? And we're going to see this runs quickly. All right? Now, the only thing I changed there is that. Now I'm going to call my method each time. Didn't change anything. Still running through 100,000 times. I'm going to still print out count at the end. What's count going to be at the end? Well, here we'll keep incrementing count in here. So count will be 100,000 at the end. But we'll see this program does not run anywhere nearly as quickly. Definitely had a pause, right? Let's kick this up to 1,000,000 times. Comment out my call to my method. So this is no longer actually getting called, it's just a comment. So we'll count 1,000,000 times. Pretty quick. Now we'll call my method the 1,000,000 times in there. Still going. Clearly not as quick. Punchline there is that I/O, printing stuff to the screen, is very, very, very expensive. So every single time we display something to the screen, it takes a lot of time. Because displaying stuff to the screen actually interrupts the computer's processor and diverts that information over to the input-output system of the operating system to actually display something through the graphics card. So there's a lot of heavy lifting that goes into actually displaying something to the screen. I'm not saying don't do it. I'm just saying be aware that when you display a lot of things to the screen, especially inside of loops, it will drastically slow down your loop from a performance perspective. More of just trivia knowledge to be aware of. Okay? Go ahead.
Why doesn't it just count how many times it wants you to say hello and then print it that many times?
It actually sort of does. It does something called unrolling the loop. So realistically, internally, it's probably at least quadding this, where it's probably breaking it down into fourths. So instead of it running 1,000,000 times, it's probably running through 250,000 times. But it's still slow, because the compiler has to try to make a guess at what's the best way for me to handle this. And depending on how many cores your processor has and things like that, that decision is kind of a randomish decision, let's say. So to an extent, it does do that. But still, every single time you display something to the screen, it takes, whether you're displaying 1 thing or 10 things, displaying 10 things takes as much time as displaying 1 thing 10 times. I guess within reason, except for the amount of time it takes to re-grab the graphics card and that kind of stuff. But generally speaking, I/O is slow. So anytime you're going to be reading or writing from a disk, or reading and writing to the screen, reading and writing from the disk is even a bit slower, but reading and writing to the screen, that is far, far slower than just doing internal math. Doing internal math, processors are great at that. Okay? In fact, the only reason it took as long as it took is because we finally did a print statement at the end. If we didn't do that print statement, that program would have basically run as instantly as a human can perceive. Because counting to 1,000,000 for a computer is nothing. So trivial. Because computers, that's what they do. They do math. Make sense? So something just to kind of keep in the back of your head from when you're writing programs, that having a lot of verbose output, especially inside of loops, is going to drastically slow your program down. Not necessarily a problem. It's not necessarily wrong. Just don't be surprised if programs that have a lot of output are slower. Just kind of some knowledge for you to keep. Okay, now let's look at a method that has some parameters. So I'm going to write a method here. Again, we're going to put static out front because that's what we do. For right now, we always put static out front. This guy's going to return an int. Actually, I'm not going to return an int yet. We're going to have it be a void. This guy's going to be called display int. And he's going to take an int a as a parameter. So now he takes a single input. And what's he going to do? He's going to print out system.out.println whatever parameter was passed to him. So here's a method named displayInt. It returns nothing. It takes an integer as a parameter. And what does it do internally? It prints out whatever was passed to it. Make sense? Class method? Yes. Why? Why is this guy a class method? Static. As static in its definition. This is the method definition. How do we call class methods? How do we call a class method? Now we define it using the word static. How do we call it? We call class methods using the name of the class in which the method was defined. Remember how I told you a little bit ago that it was going to be ingrained in your soul? It has begun. These are going to be little mantras we're going to say over and over and over again. All right? So we call class methods using the name of the class in which the method was defined. This method was defined inside of the driver class. So I'll call it by saying driver dot displayInt. You'll notice that Eclipse figures it out for you. After I said driver dot, what did it do? When I said driver dot, it gave me a list of options. I can call display hello, I can call display int, so I'll call display int. And display int requires that I pass it a single input of type integer. So I must give this guy an int in order to work. So I'm going to go ahead, I'm going to pass him a 5. 5's an int, right? So this guy is going to display 5. Similarly, I can call that exact same method, but pass it a 9. And now it'll display 5 the first time and 9 the second time. Because 5 is getting passed into A, and A is getting displayed. The second time through, 9 is getting passed into A, and A is getting displayed. That make sense? The purpose of the parameters? It allows me to write a method generically, do something to this parameter, and then I can pass it different parameters to get different outputs. So if I run this, I'll get 5 and 9. Go ahead.
So if now after that you put system out println a, will it give you 9?
Put it where? Here?
Yeah.
Okay, good question. The answer is no. Why? This is related to what we talked about last class.
Is it because you defined it in the method?
Yeah, a scope. Remember we talked about variable scope last class, where variables is accessible. A is a local variable to this method. It lives and dies with this method. So A does not exist up here. We can force 9 into A by passing it as part of the syntax for a method. But A lives and dies with this method down here.
So how do you know when you've localized a variable or not?
A scope is created associated with a method. So all methods have their own scope. So anything defined inside of the parameter list of a method would be a local variable whose scope is local to that method. So just like main has a single parameter that comes in here, that parameter lives and dies with the method main. If we define variables inside So this is actually an interesting way of explaining this. I'm going to say int a equals -3, pass in 5, pass in 9, and here we'll even make it creepier. I'll pass in a. Display int takes an integer as a parameter. It does not matter what this integer is called. I've named it a, but I can name it that. As long as whatever I name it there, I use there when I refer to it. That makes sense? Okay, but it's extra confusing if I leave it as an a here. So up here in main, I'm going to define a local variable named a. So this variable is even more local than this guy up here. Okay, he is local to this expression, this block expression right here. Okay, I'm going to call my display int 3 times. First time I'm going to pass it a 5. Second time I'm going to pass it a 9. Third time I'm going to pass it a. Then I'm going to print out a. Well, this guy takes an int a as a parameter. What's the output of this program going to be? It's going to print out 4 lines. What are those 4 lines going to be? 5, 9, -3, -3. 5, 9, -3, -3. Why the 5? Well, I'm calling the method once here, passing in a 5. 5 comes in for a. System.out.println a resolves to its value, which is 5. The value of this a, not this a. Next one, 9. Call the method, pass in 9 for a, print out a resolves to its value is 9. Third time, call the method again, pass in a. A is a variable. That variable resolves to its value, which is -3. So we're actually passing in a -3 here. -3 comes into this variable named a. Then I print out a, which prints out a -3. Lastly, system.out.println a. A is a variable. All variables resolve. So this is an interesting statement to throw into variable blah, blah, blah. Variable resolution. All variables resolve to their most local definition. All variables resolve to their most local definition. Okay, so the most local definition of a here is this local variable named a, which is -3. The most local definition of a here is the local definition of a, whose value is -3. The most local definition of a here is not this guy. In fact, this guy and this guy are not even in the same scope. So even if this was called C, it would say I've never heard of a. Because this is a method, this is a method, this is a method. Everything inside of this method lives and dies with that method. Everything inside of this method lives and dies with that method. Everything inside of this method lives and dies with that method. So the local variables of this guy don't cross over to these other two. So me trying to print out a inside of display int, because I changed this value to C, it's going to say I've never heard of this guy. Because this a isn't part of the scope that this guy lives in. If I were to define, I'm telling you eventually we will be able to do this, but we don't know how to do it yet. But if I were to define a variable at the level of the class, outside of the methods, but inside the class, those variables would govern all these methods. So then I could have a variable named a defined up here. Okay? Does that make sense why this works this way? So why we're getting 5, 9, -3, -3? All right. Let's create another method. Static, void, print, multiply. We're going to have this guy take in 2 parameters. Notice it's comma delimited. Parameter 1, parameter 2. Every parameter has a variable name, and it has a type associated with it. So this method is called print multiply, and it expects 2 inputs for it to work. An int followed by another int. Make sense? Okay. And what are we going to do? We're going to say system.out.println A times B. So it's a class method? Yes. How do you know? Static in the definition. So we'll go ahead and call this method. So we'll say driver dot display multiply, because we call class methods using the name of the class in which the method was defined. We're going to pass it 2 values. We're going to pass this guy a 5 and a 3, and it should print out a 15. Because 5 is going to come in for A, 3 is going to come in for B. 5 times 3 is 15, and that's what will print out. Call it a second time. Pass it a 10 and a 5. 10 and a 7. Yeah. That'll print out 70. $15 and 70. Make sense? All right, I wrote another method called print multiply that takes 3 parameters, int A, int B, and int elephant. And this guy prints out A times B times elephant. So I'll call it 10, 7, and 200, and we'll see this works. So it's my 14,000. But interesting thing to notice here. I have a method here called print multiply. That's a class method, correct? I have another method called print multiply. That is a class method. They both return void. I have 2 methods with the exact same name. Why is this okay? How can Java differentiate these guys? Number and or type of inputs. So this actually has a fun name associated with it. I think I probably said the first day of class something about that technology is filled, well, really higher education is filled with hard things that have really scary, or easy things that have scary names. Did I say something about that? Yeah, it's something I talk about pretty often. That people try to make themselves sound smarter by using big words. Know what I'm talking about? So here's one for you. Polymorphism. That sounds scary. Must be something difficult, right? Polymorphism means there is more than one method with the same name, but a different number and or type of parameters. Polymorphism is a scary word that means having more than one method with the same name and have it being okay. It's an object-oriented term, polymorphism. Oh, man, put myself to sleep here. Can't even imagine what you guys feel like. I know. I do need caffeine. To hunt some down during break. Somebody's got to be in charge of bringing me coffee. It can only benefit your grade. Last semester when I taught this class, like I told you, I had a couple of students that commuted from Chicago. So we had, I don't know, it was like 25 people in the class. This class is so small because this is the first time we're offering this course in the spring. We're going to start doing this in the spring and the other course in the fall. But now, for this semester only, we haven't put it up yet. We're going to announce it. So for those of you who this night works, the second 8 weeks, so after this class is over, we're going to do the course that this is the prerequisite for, the 537 class, the second 8 weeks. So if you're a glutton for punishment and you want to, when it's still fresh in your mind, you want to just keep going because it literally picks up where this class ends. It just keeps going. You'll have an opportunity to take that this semester if you would like. It's like we're only doing it this one time because we're switching the order those classes are offered. So this is that transition year. That's why this is a small group. Usually we have like 25 or 30 people in the class. We did. Second 8 weeks last semester. But I had a couple of students from that class who commuted from Chicago and they brought me food. From Portillo's. Love Portillo's. Only benefited their grade, I promise. All right, so polymorphism. Scary word for something easy. So how does Java know which of these we mean? Well, the 2 times I called it up here, passing it only 2 parameters, it calls the version of print multiply that takes in 2 ints. The one I called passing it 3 parameters, it calls the version of print multiply that takes in 3 ints. That make sense? Well, what if I create a print multiply that takes in 2 parameters, but the first one's a char, and the second one is a int, maybe called times. And let's say this guy prints out C some number of times. So, for example, let's say that I wanted this guy to print out, let's say, for example, C was an A, and times was 6. And I wanted the output to be A 6 times. Understand what I'm trying to accomplish? How would you write that code? Take about 3 minutes. I'll wait. Think about how you would write the logic in here to take whatever character this is and display it all on one line this many times. Okay, so take about 3 minutes to think about that, and then I'll show you the solution. Actually, I should go steal some caffeine while you're doing that. Good thinking.
So guys, let's work together. I'm just kidding, but yeah.
What'd you say?
I was joking. I said we should work together, but I was just kind of joking.
Not a joke.
All right, so let's take a loop at this. So I'm doing something some number of times, so it's probably going to be a loop, right? Do I know how many times I'm doing it? I'm doing it times number of times, right? In our example here, times was 6. So I'm doing it times number of times. So when we have a looping problem where we know how many times we need to loop, which a loop lends itself to that type of problem? For loop. So I'm going to do a for loop. For int I is equal to 0, I is less than times I plus plus. What am I going to do each time? I'm going to say system.out.print C, whatever that variable holds. Then at the end, I'll say system.out.println. And I can just do empty string or something like that to kick it down a line. All right, so this loop goes from 0 to times, not including times. So it'll go through a total of times number of times. So if times was 5, we'll go 0, 1, 2, 3, 4. That'll be our 5th time. All right, each time through, I'm going to do system.out.print whatever char C holds. But I'm using print, so it just prints it on the screen, but doesn't hit a carriage return. We'll do that times number of times, and then we'll finally break out of our loop, and I'll just do the carriage return at the very end. Make sense? So now if I come up here and I call it, we'll do our A 6 times. Go ahead and run it. And we see our 6 A's display there. If I want to do A 600 times, it's going to be more interesting. There's A 600 times. Now, what's interesting here is we have we have 3 versions of print multiply now. 2 of the versions both take 2 parameters. The first one takes 2 ints. The second one takes a char and an int. So that goes back to this slide where we talked about polymorphism, meaning there's more than one method with the same number, with the same name, but a different number and or type of parameter. So this guy has the same number of parameters as the different one, but we can tell it apart because the types are different. This guy takes in a char and an int rather than an int and an int. Make sense? All right.
I didn't. Wait just a second.
Okay, so that's a whole bunch of different versions of print multiply. We could have named that whatever we wanted, but just to get an idea on how polymorphism works and how we could have more than one method with the same name. This won't necessarily be super common, but sometimes you'll want to perform the same task, but maybe with different kinds of inputs. Sometimes you will have something already packaged into something, and you want to do something with it. Other times you might need the individual pieces, and you'll package it up internally and then do something with it. Make sense? Now we can get really interesting here. Oh, hold on. Before we do that, I gotta do something else.
Why'd you use why'd you use the apostrophes instead of quotation mark?
Right here?
Or on the A, yeah.
That makes it a char.
But,
Single quote, char, single quote, designates it as a char type.
never mind.
You were saying that instead of this.
Yeah, because that would.
These are strings. We're going to talk about strings the whole second half today. But the single quote, A single quote is the literal value for a char type. Now, I'm going to write another version, another method here. Let's write a method that actually returns a value now. So I'm going to create a method. Here, I'll do it at the very bottom just so we keep going in order, but it doesn't really matter. Static. This guy's going to be return an int. We're going to say do multiply. This guy will take an int a and an int elephant as a parameter. I like to throw the strange variable names in there just so you don't get accustomed to thinking everything has to be A's and B's and C's. Whatever variable name you want is fine. Just make sure whatever you call it up here is how you use it inside. And this guy is going to return A times elephant. So now we have a method named doMultiply. This guy happens to take two parameters, but he actually returns a value. He returns an int rather than all these other guys that have not returned anything. We've advertised them as returning void, which means return nothing. It's fine to have a method that returns nothing, but you must tell Java you intend to return nothing by putting a void there. So if you have something other than void, make sure you return something. If you have a void there, make sure you don't return something. Don't say void and then try to return crap. It won't work out well. So this guy returns an int. His name is doMultiply, takes two integers as parameters, and we're going to return the two integers multiplied together. Now this guy is a class method, right? Static out front at its definition. We call class methods using the name of the class in which the method was defined. Driver dot doMultiply. We'll pass this guy a 12 and a 13. Well, here, let's do a 12 and a 10 so the math's easier. What would the output of this program be? $120? Okay. Why is the output nothing? No what? Never told it to print anything. I told it to call the doMultiply method, passing it two numbers. What does doMultiply do? Takes those two numbers, returns those numbers. Those numbers come farting out the back here. Little elementary school boy humor. Okay, so that 120 comes firing out of this method there, and we absolutely do nothing with it. We're getting the 120, but we're not doing anything with it. I could capture it inside of a variable. I can say int val is equal to that. I can run it now. Still not doing anything with it, right? I'm capturing it inside of a variable, but I'm not printing the variable or doing anything. I could say system.out.println val. And now I'll get my 120. Because this guy boiled down to 120. I stored the answer inside of val. Now I'm going to print out the value stored in val. So I'll get my 120. Similarly, I can just print it out directly. So let's do 8 times 6. So I'm going to system.out.println. What am I printing? I'm printing out whatever this boils down to. Calling doMultiply, passing in 8 and 6 should give me a 42. 48. All right. So there's my 120 and my 48. Now, what's the advantage of doing it this way as opposed to doing it this way? Or, when would I use each of these methods? When would I capture it in a variable and then print out the value of the variable versus just print out the value that's returned by it? Go ahead.
You're gonna use the variable again later on. Then you'd want to capture it in the variable.
Yep. So, concept is this. I don't need a variable unless I intend to use it more than once. If I'm only going to do this math and print it out, don't waste your time, don't waste your computer's memory with a variable. But if I'm going to call this method and get an answer, and I'm going to print out that answer, but then later on I might use that answer for something else, now we need to store it in a variable. Otherwise, you're going to have to call the method again for it to do the calculations all over again. That makes sense? So, store something in a variable when you need to use it more than once. Otherwise, don't waste the memory or your time. So up here, we're capturing it in a variable, printing out the variable. Down here, we're just printing out whatever it boils down to without capturing it inside of a variable. Make sense? Okay. What would the output of this program be? Print out a Q? How many times? 26 times. So we're calling the print multiply method, this guy right here. That's this particular version of print multiply, the one that takes a char followed by an int. The char I'm passing that guy is a Q. The int I'm passing him is whatever integer this guy boils down to. That is, I'm calling do multiply, a different method. Passing it a 13 and a 2. Here's do multiply. Do multiply is going to take in a 13 for A, a 2 for elephant. It's going to return those two multiplied together. So this guy is going to boil down to an int. In this case, it's going to be the int 26. Correct? So what I have highlighted right here will ultimately boil down to 26. That's what it will become. So this should print out Q 26 times in a row on a single line. Make sense how that worked? All right. We could not get our second parameter here until we resolved this call to this method. So everything was put on hold. We started calling the print multiply method, passed it its first parameter, which is a literal. It's a hard-coded char, a Q. Done. But the second parameter needed to be computed before we could use it. So we had to put the call on hold and go and compute this guy. That make sense? Okay. So let's do an interesting problem. Factorials. Little math problem. So for instance, 4 factorial is 4 times 3 times 2 times 1, right? So 4 times 3 is 12, times 2 is 24. So this guy ultimately boils down to 24. 5 factorial is 5 times 4 times 3 times 2 times 1, which is what, 120? Make sense? That's what factorials are. So we're going to go ahead and write factorial. Static int factorial takes in an int n as a parameter, and we're going to calculate n factorial. Well, how are we going to do this? Again, this is what factorial looks like. So if we passed in a 4 for n, this guy should spit out a 24. How would I do this math?
Is there like some convenient math stuff?
No, only using what you know in the class so far. Only built-in crap. Go ahead.
You take it and then you times it by the thing minus 1 and stuff.
Times it by the thing like minus 1 and stuff. It's definitely an unambiguous solution.
It's a lot.
Okay, we're going to want to do something multiple times. We're going to need a loop.
Yes.
How many times are we going to loop? N times? Okay. So start off, we're going to do this n times. 1, 2, 3, 4. So we're going to say 4 int I. You want to start off at 0? Why don't I start it off at 0 and then you can change it when you see how it should be changed. So we'll start with our stock loop. I want to loop through n times, so I'm going to start I off at 0. I'm going to keep going as long as I is less than n, and each time through I'm going to increment I by 1. And stuff. All right, make sense? What do I want to do each time through this loop? I'm going to need something to accumulate my answer in, right? All right, so I'm going to create an integer called answer. What do you want to start answer off at? Start off at 0? Oh, good. Something we're going to be looking at here is solution patterns. Our little lesson here we'll finish up our first half with. We're going down a very good wrong path for our solution patterns. So, so live it up to our expectations. Perfect. We're going to be doing multiplication, right? Okay, so since we're going to be building something on multiplication, our pattern typically says start with a 1. You multiply anything by 0, it's going to still stay 0, right? But 1 gets us kind of rolling with multiplication. So most solution patterns for solving problems that involve accumulating something through multiplication usually is going to have you start with a 1 as your starting point. Okay, now if you look, go ahead.
Could it work if you put, and I'm probably thinking, I can't quite hold my train of thought, but if you put for int and then I equals n and then I is greater than 0 and then I minus minus, would that have the same effect?
Yep.
Oh, okay.
So she wants to do this. She wants to start I off an n, keep going as long as I is greater than, you said greater than or equal to 0?
Just greater, oh, is it greater than or equal to?
Doesn't matter. You want to say greater than 0 for right now? I mean, it matters, but it won't matter in terms of the correct solution in this case. It'll matter whether or not we waste our time multiplying by 1 a couple of extra times. We'll see it. But we'll say greater than 0 right now, and then you want to subtract 1 from I each time. So we'll start off at n, then it'll be n minus 1, then it'll be n minus 2, then it'll be n minus 3, until we run out of n's, right? And what are we going to do each time? I want to accumulate this. First time through, if n is 4, I'm going to take 4 and I want to multiply it by what? What do I need to multiply 4 by in order to get 4? 1. And 1 just happens to be inside my answer. Answer is equal to answer multiplied by n. So the first time through here, I is, let's just assume for this particular run, n is equal to 4, just for our example. Okay? So if n is 4 in this particular run, I will start off at 4. Is 4 greater than 0? It is. So we'll say answer is equal to whatever answer currently is, which is 1, times 4. So now answer will be equal to 4. Right? Decrement I, so 4 becomes 3. Is 3 greater than 0? Yep. Answer is equal to whatever answer currently is, which is 4, times 3. So now answer is 12. Decrement I, 3 becomes 2. Is 2 greater than 0? Yep. Answer equals whatever answer currently is, which is 12, times 2, which is 24. Then decrement I is now 1. Is 1 greater than 0? Yep. Answer is equal to whatever answer currently is, which is 24 times 1. Great. So the answer is still 24. I minus 0. Is 0 greater than 0? Nope. So we fall out. We have the right answer, but we multiplied by 1 an extra time. Would this still work if I said greater than 1? 4 times 1 is 4. 4 times 3 is 12. 12 times 2 is 24. 2 becomes a 1. Is 1 greater than 1? It's not. We fall past, but we have our correct answer. Why run through that 1 extra time just to multiply what we already have by 1? Make sense? It's not incorrect, just inefficient. So at the very end, notice that this guy's screaming at me right now. I got the little red underline. Why? Because I've told him I'm going to return something. Yet I haven't returned anything in here. So I'm going to go ahead and after the for loop, I'm going to return answer. Now a caveat I'll throw at you here, not related to factorial, but related to returning things. When you tell Java that you will return something, you must return something. And the reason I harp on that is sometimes you will have a method that looks like it will return something, but it doesn't actually return anything. So, as an example, I'm just going to write a quick little method. Make this guy return a Boolean called blah. Takes no parameters. For int I is equal to 0, I is less than 1,000, I plus plus, and here we'll have this guy taking an int m as a parameter. As an example. Am I returning something here? It's Boolean, isn't it? Yet Java's screaming at me. Why? True is a hard-coded value. M is a local variable. Came in as a parameter. Here's my for loop. I'm going to go from 0 to 1,000. And if I is equal to m, I'm going to return true. Why is it screaming at me? It's going to say this method must return a value. But I am returning a value, aren't I? The answer is maybe not. Why am I maybe not returning a value here? It's related to how, actually it's related to two things. There's two good reasons. One of it's related to how for loops work. The other one's related to how if statements work. Okay, tell me more about that.
Let's go. keeps the return inside it. That doesn't really explain it.
Yeah, I'm not quite there yet. Okay. Are we guaranteed to get to this line? No, for two separate reasons. One reason is we may never have a situation where I is equal to M. And if that's never true, we never return true. Secondarily, for loops are pre-check loops, which means there's no guarantee that we will execute the body of this loop even once. Now, as human beings, we can look at this and say, okay, look, I starts off at 0. I know the very first time 0 is less than 1,000. We're cool. Okay? But Java has to write itself generically. It's not going to sit there and figure out the semantics of the program you're writing. It's going to sit there and say, okay, this is a for loop. For loops have no guarantee that they will execute. As an example, this method must return a result of type Boolean. Can you tell me as a human being with 100% certainty, will I get to this line? As a human, you can tell me that because you see that I starts off at 0. You know for a fact 0 is less than 1,000. So you know we're going to hit this line the very first time. We know that because we can do the math, right? And return statements make methods immediately end. So as soon as we hit that return statement, the method's over. We won't go through a second time. Java does not know that. Java says, look, this is a for loop. For loops are pre-check loops. You better have a backup plan. Even though we know as a human being we will never get to this line, Java requires us to have a line that could be reached in the event that everything went wrong. So the lesson here is that if you tell Java you're going to return a value, you must return a value under any circumstance for that method. Just because as human beings we know we will hit that line, Java doesn't necessarily know that. So you'll have to have that extra return statement out here, even if you, I mean, this is stupid logic. We'd never write something like this, but even if you did, Java is going to require us to put this useless return statement out here because we happen to know because of the nature of the problem we're solving, we will always get inside this loop.
Still complaining about.
It's not complaining anymore.
It's got the little yellow one.
Where? Oh, it's because it's saying we've never used I, we never used M. So this is just saying you didn't use this variable.
Ah, okay.
Just as dead code.
Alright.
Yeah, it's not incorrect, just we're wasting a lot of time in this one. There's a lot of code that does nothing. Kind of make sense? Okay, so then quickly, here's an interesting, let's see, what are we doing on time? No, let's go ahead and take a 15-minute break. We'll come back at 8:20, so 16-minute break. Stretch it out, go to the bathroom, whatever. I'll get the video uploaded. We'll come back. I want to talk about a recursive version of factorial, and then we're going to talk about strings. All right? So I'll see everybody in 15 minutes.